All right, where we left off is we ran all this code and we got this print off of the results of our ANOVA F test. And out of all this stuff, all we're going to look at is our F statistic. And the F statistic is a number that the bigger it is, just think of it this way: the bigger it is, the less likely it's going to happen by chance, and the more likely our null hypothesis needs to be rejected. And so it puts together the difference of the means as well as the standard deviations in those groups, and comes up with this F statistic. And then more importantly than that is this the probability that we would get that F statistic or an even bigger one. In this case, this p-value 1.47 e minus 0.06 means, and let's see if I can write on here. Let me give some text here, just so I can write. So that, where did that go? Down here. So the 1.47 e negative 0.06, that's scientific notation for 0.000000147. Let me see if I did that right. So the minus 0.06 means I'm moving the decimal place from between the 1 and the 4, 6 places to the left. So 1, 2, 3, 4, 5, 6. Perfect. And one way I remember that when it's getting to be a really, really small number, because this is a negative exponent, the number of zeros, if you count the 1 before the decimal place, should be equal to this number. So I've got 1, 2, 3, 4, 5, 6 zeros, and that corresponds to the 6 decimal place moves from where it was originally over here. Okay, so however I slice it, that's way less than 0.05. So we have significance. Yay! So if I look over at my slide, go to slide 2, here's all that code that I was trying to describe. And here's just the part of that results that we're super, super interested in. And the most interesting part of it is this p-value. So I'm highlighting that p-value and just saying it's less than 0.05, and then writing out the conclusion. There's enough evidence to support that not all the means are the same. That was our alternative. We are rejecting the null hypothesis. And so we're saying there's enough evidence to support the alternative. All right, there's one more piece to this that I'm going to try to fit in this same video. So because I have significance, I know that not all the means are, or at least I don't know, but I have enough evidence to support that not all the means are the same. But precisely which means are we talking about? So when I'm looking back up here, I was thinking that this contact lens mean was quite a bit lower than the neither mean. So I'm going to guess that these two are significantly different. But what else? Like, are there other pairs of categories that have significantly different means? That's what we're going to figure out now in what's called a post hoc test. So after we run the test, after we have significance, we're going to find out where that significance comes from and do a pairwise comparison between two categories at a time to see which ones are significantly different from each other. So what I've done here, I'm going to get rid of this. I don't need that. But this first piece is kind of important to do some of the other stuff. So all this is doing is saying, make a subset of the data frame that only has these two variables, and drop any rows where either one of these has a nan. So I'm only going to look at the people that had a sibling number in there that I haven't data managed out, and then an eyewear category that I haven't data managed out. So, and these are the only two variables in this data frame sub 1. Then what I can do is I can run a group by command to look at the mean sibling numbers, look at actual numbers, and then also their standard deviations. And this gives me a better sense of what the means that are being compared and what the standard deviations. Notice how low the standard deviation for contact lenses was, and we kind of noticed that in how spread out this was. So we're just getting a little bit more detail in what we're seeing. But the actual report that we're going to use and analyze, we've got another import statement. So import stats models.stats.multicomp. It's a mouthful. So we're going to import that as multi. And then we're going to do MC1, which is the mean comparison. We're going to do a pairwise two categories at a time comparison of those means. And so it's this multi comparison. Notice there's a capital C and a capital M in that multi comparison. Parentheses, sub 1, that subset of the DF that I created, sibling number, comma, sub 1 eyewear. So these two statements are very similar to the DF bracket bracket quotes variable name that we've been doing throughout this whole semester, but now we're using sub 1 instead of DF. And we have to put the quantitative variable first and the categorical variable second. Then our results are going to be this MC1 dot Tukey HSD, and that's just fun to say. It's not turkey, it's Tukey HSD. I'm sorry, I'm just amused by the name of this post-hoc test. And there's all sorts of post-hoc tests for this, but the materials that I had that showed how to do it in Python use Tukey, so I'm using Tukey. And then you print the summary again like we did before. So when I look at that, it's going to be actually a lot of stuff, but relatively easy to read. Notice that it gives an adjusted p-value. It has to adjust it because, it's the regular p-value kind of looked at everything all together. We need to when we're just looking at two at a time, we actually need a smaller p-value. But they've already adjusted these accordingly. And they already tell us whether it's significant or not. We don't have to judge whether it's smaller than the significance alpha that we need to use. So we just look over here whether we need to reject or not. And so it's these two categories that we're rejecting. These two pairwise categories that we're rejecting. So when I look over on my slide, to that third slide, here's all the code, but I'm highlighting the p-value and the fact that this is true, and then underlining the two categories that we found had significantly different average sibling numbers. So both and neither, and then contact lenses and neither. So my conclusion, I worded that with the average number of siblings is significantly different between the both and neither categories and between the contact lenses and neither categories. And that's it. And I should probably change this just a hair. And so what you'll see when you actually go to this slide, because I'm changing it right now, is this is going to be a little bit different. We have evidence to suggest the average number of siblings is significantly different between, because in all these tests, we don't know for sure. As unlikely as it might be that even with a small chance that we just get some sampling variability, that's super unlikely. It's possible. It's possible, and that's where the type 1 errors come that you reject. Here we are rejecting the null hypothesis, and it might be true still. Just because we're rejecting it, just because we have a low p-value, just means we have evidence enough to reject it. not that we're sure. So I kind of need to be careful with my language. So we have evidence to suggest that the average number of siblings is significantly different between the both and neither categories and between the contact lenses and neither categories. And that's it. All right. Take care. See you later.